Watch this single keystroke. A developer is typing a standard git push command to upload their code, but by adding one semicolon to the end of that text, an attacker could silently gain read and write access to millions of private repositories. This exploit was discovered inside GitHub's internal infrastructure by Wiz Research, tracked as CVE 20263854. It is a critical remote code execution flaw. The vulnerability carries a high-severity CVSS score of 8.7, affecting GitHub.com, the enterprise cloud, and self-hosted enterprise servers. To see why this matters, look at GitHub's multi-tenant architecture. On this platform, millions of different users share the same underlying hardware. A single backend server node houses hundreds of isolated repository blocks. Because of this shared storage, an attacker who can compromise one repository on the backend gains lateral access to every other repository hosted on that same node. This didn't require advanced hacking tools or specialized software. Any authenticated user with push access to a single repository could trigger the exploit. Shared cloud infrastructure relies on the absolute isolation of user data. When a microscopic flaw allows data to cross those boundaries, a single localized breach can compromise millions of unrelated users. The attack chain begins when a developer uses the git push-o command. This is a standard way to pass text options from a local terminal to the server. Before the server farm, the request passes through an internal proxy called babel.did. It takes user options and embeds them into an internal network header called xstat. The xstat header uses semicolons to separate different fields of data, treating every semicolon as a physical wall. GitHub's oversight was simple. They didn't filter the incoming text for semicolons. If a user included one in their push options, the gatekeeper passed it through without sanitization. This meant a user-typed semicolon would sit directly inside the xstat network header, mimicking the system's own internal structural punctuation. When downstream services read the header, they see the user's semicolon and interpret the text following it not as a user option, but as a trusted command. By skipping a syntax check, GitHub allowed standard text strings to function as internal delimiters, giving an attacker the ability to manipulate the server's logic. Once the malicious semicolon is accepted, the attacker can begin overriding specific variables to dismantle the server's security. First, the attacker overrides the Rails end variable to bypass sandbox restrictions. Next, they target the custom hooks dir variable to redirect the system's search toward a directory they control. Finally, the server runs a malicious binary file, resulting in full arbitrary code execution. This chain reaction shows how command injection turns a system's own rigid logic against itself, escalating a single string of text into a total backend compromise. GitHub patched their hosted cloud services within hours of receiving the report. Because they control that infrastructure, they were able to verify that no one had exploited the flaw before the fix. However, the situation was different for GitHub Enterprise Server. These are privately hosted instances managed by individual companies, which must be updated manually. The scale of exposure was significant. At the time the vulnerability was made public, 88% of these corporate servers remained unpatched and vulnerable to a takeover. While centralized cloud platforms can be secured almost instantly, self-hosted infrastructure often faces a dangerous delay between the release of a security patch and its actual implementation. This discovery also highlights how modern security research is changing. Wiz researchers were able to find this flaw deep inside closed-source infrastructure that is normally hidden from view. They used AI-augmented reverse engineering tools to probe the platform's internal code, mapping out the system's behavior from the outside. These tools allow researchers to analyze complex systems much faster than human eyes alone, identifying legacy syntax flaws that have gone unnoticed for years. As AI-driven tools make it easier to map the logic of closed-source systems, legacy flaws, even a single misplaced semicolon, are increasingly likely to be identified and exploited.